So if we take what we just learned about electrostatics and we take it to the next level, we can apply it to electric circuits and why electric circuits work the way they do. So let's imagine I've got these two charged plates, right? They're just plates of metal, whatever, right? And I put a bunch of positives on one side and I put a bunch of negatives on the other. All right? What should happen? They should attract, right? But what we've done is we've put this thing in here called a dielectric. And what a dielectric does is it does not allow charge to flow between whatever it is between them. Does that make sense? It acts as a barrier. So you can't get charges hopping across. But they really, really, really want to be near each other. They're attractive, right? They want to be near each other. But they can't get there, right? They want to balance out, right? They want to be neutral overall. This guy is really negative. This guy is really positive. But they want to balance out. They want to be even, okay? But this dielectric is not allowing them to. Does that make sense? Okay? But if I were to take a wire and connect them, now do we have a path for them to flow and balance each other out? We do, right? Now we have a way that these negatives can run through to the other side, and overall these two things can be neutral. Okay? But if I put a light bulb in the way, in this wire, right? All of a sudden, it lights up. Does that make sense? Right? So, this attraction between opposite charges is what's going to cause these negatives to run through to the other side until both of these plates have the same exact charge. Okay? And if we put something in the way that could use these electrons, it'll do work for us. Does that make sense? So if we put a light bulb in the way, now the light bulb lights up. If you have an electric circuit, you need a complete path for electricity to flow. Does that make sense? So when you're talking about a light bulb, it's hard to see. You can't really see it. But in a light bulb, this filament, this little wire in here that's coiled up, is actually just a wire. And it connects to the side of the bulb on one end, and then the other end connects to the bottom. So if you had two things like connect here, nothing on the bottom, right? There's not a complete path. So if you took your battery and it connected like this, right, touching here, and then you had the wire go around like that, that would light up, right? Right, because now you have this path for it to flow through. If you flipped it and you put the battery on its side and then you had the wire run to the other side, that would work too, right? But you need that complete path. So if you had if you had the battery touching right here, and then the wire here going someplace else, it wouldn't work. Okay? Because you have now taken this piece out of the battery if you don't have anything connected right there, and you don't have a path for it to flow. Okay? So the biggest, most important thing with electric circuit is if you want electricity to flow and you want it to work, you need to have a complete path. Okay? If there's any openings, it doesn't work. So before we jump into electric circuits and types of circuits, there's a few diagrams we need to know. Okay? That's a battery. Okay? So in a diagram, if you see either long, short, or just long, short, battery. Okay? This means a battery or voltage source. Okay? If you see something like this with squiggly lines, this is a resistor. That's not very good, but that's okay. This would be a light bulb. Typically, you don't draw a light bulb like in a circuit diagram like that. You just draw it as a resistor. Right? A resistor is something that's going to use the electricity. Okay. This is a switch. If you think about it in your house, when you flip a switch, all you're really doing is you're opening or closing a circuit. Right? Because if the circuit is open, electricity is not going to flow. And that's literally all the switch is doing in your house, is it's connecting and disconnecting two pieces of metal. That's all it's doing. It's completely mechanical. There's nothing special about it. Right? But super useful. We could have just a wire. Straight lines are just wires. Right? It's just connecting things so that electricity can flow. Good? Okay. All right. So let's throw all of this together. You have two types of circuits. The first could be a series circuit. In a series circuit, all your resistors, light bulbs, whatever is using the electricity, they're in a line. They're in one single path. Okay? So if I've got my battery, light bulb 1, light bulb 2, light bulb 3, this would be series. In order for the electricity to come out this side and get to the other end, it has to go through all of them. Does that make sense? Okay? So this is, because you've got three different resistors, this is series because they're all in a line. They're all in a path. Okay? Now, normally I'd have you build these circuits, but in the interest of time, I'm not going to do it. So characteristics of a series circuit. The total resistance in a circuit is equal to the sum of the individuals. So if I want to know, this battery, it doesn't see three individual resistors. It just sees everything as one thing. Does that make sense? It just sees these three as one total resistance. So if I want to know what the total resistance is, I'm going to add the three of them up. So if this is 1 ohm, 1 ohm, 1 ohm, the total resistance of the circuit is 3 ohms. Okay? The total voltage, meaning the total amount of push, is equal to the sum of the three. Meaning, this resistor is going to use a little bit of the voltage, then this guy is going to use a little bit of the push, and then this guy is going to use a little push. It's like you're getting tired after you push them. Does that make sense? Okay? By the end, if this is 9 volts, you got 9 volts here. By the end, you have no volts. Okay? These three have used them all. And we'll get to that shortly. That's part of Kirchhoff's laws. And the total current in the circuit is equal to the current through any of them. If we go back to our water flowing analogy, you've got all this water coming out here, right? Well, in order for the water to get to this resistor, it has to flow, all of it has to flow through here, correct? To get to here, it all has to flow through the other side. Does that make sense? Yes? No? Maybe so? Okay. So, all this water all has to go through everything before it goes through again, before it gets to the other side. Okay? These are really important. Okay? Knowing the characteristics of these circuits. Okay? Oops. Correct. So there's your series circuit. The other type of circuit you can have is a parallel. In a parallel circuit, your resistors could be connected in separate branches. So in this case, electricity comes out. It's going to hit a fork on the road. Some will go here, some will go there, some will go to the other one. Okay? Pretty obvious the difference between the two, right? The resistance is a little different. 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus however many you have. So if you have a parallel, this is really, really, really important. If you have a parallel circuit and you want to know the total resistance, do not solve for R1 over RT. You need to solve for RT. Does that make sense? So add the fractions up and then cross multiply, take the reciprocal. Make sense? You need to solve for this, not the whole thing. Okay? The total voltage is equal to the individual voltages. So in this case, every light bulb, every resistor, whatever it may be, they all get the same voltage. Okay? In the current, the total current is equal to the sum of the individual currents. Does that make sense? So do you see how these two are flipped between series and parallel? Right, the characteristics of them? So let's visualize it. What does it look like? Here could be a series circuit, right? Here would be a series circuit. Your electricity starts here, right? And as soon as you get a voltage, you've now ramped up the energy. Does that make sense? You've ramped up the energy, and now it's flowing through our circuit. As soon as it hits one resistor, which we call 30 ohm resistor, high voltage, high resistance, it uses some of this energy, right? You could think of this as when you get voltage, you're increasing the potential energy, which is really what it is, called potential, right? You've increased the potential energy. Remember, potential energy, the higher you are, the greater the energy you have, right? Well, it's going to use, this first resistor, think of it maybe as a light bulb, it's going to use some of that electricity, right? It's going to use some of that potential energy. And because it has a high resistance, it's going to take a lot to get it through. All right? It's going to use a lot of voltage. Does that make sense? And the reason why it uses a lot is because they both get the same current. You'll notice that it's the same amount of electron, or they call them positive for whatever reason, the same amount of charges going through. Does that make sense? You good there? Okay. But because everybody gets the same amount and it's a high resistance, it's going to use a lot of voltage that's available. Then it goes through this other one, right, this 10 ohm. And because it's a lower resistance, it uses less voltage. But you'll notice that we start at 0, we end at 0 in terms of the potential that it has, the potential energy. So it uses it all. Does this make sense? It's kind of weird looking. But I think it's a good representation of what a series circuit looks like. You're starting with some potential, right? And then as you go through, some of the voltage is used as it goes through resistor, and then the rest is used as it goes through the other resistor. Albert?
So is the ramp supposed to represent the battery?
Yeah.
Because
Yep.
it gives energy. Well,
Yeah. Yep. Yeah, that's awesome. Yep. Yeah, so the ramp is kind of like the battery. That's lifting the voltage up, giving it potential energy. for it then to be used as it flows through. Okay? And again, you notice that differences in voltage, right? Because remember, total voltage here is equal to the sum of the individuals in a series, right? But in a series, if we follow like this one charge, it goes all the way through, right? So the total current is equal to the current through the individuals. Okay? Now, if we're talking parallel, everybody gets the same voltage. Okay? Everybody gets lifted up to the same height ramp. And these would be your two different branches. Now, because there are two different resistors, correct? Two different resistors, you're going to get different amounts of current flow. Greater blockage, so less charge flows through it. Smaller blockage, so more charge flows through it. Okay? Does that make sense? And again, they still go down to zero. Now, voltage, remember, it's energy, right? It's a measure of potential energy. Okay? They both get the same voltage. How long do you think this battery is going to last compared to a series? It's going to be shorter, right? Because it needs to push out more energy to keep these both going. Right? To keep them at the same height. It needs to do more work. It needs to push more electricity out. Does that make sense? Pros and cons. Series circuit uses less electricity, but greater resistance, so you're going to get dimmer light bulbs, right? Parallel circuit, if these were both the same, right? If these were both 10 ohms, these light bulbs would be the same brightness, and you'd get, but they wouldn't last as long. But the nice thing about parallel circuit is, let's say I cut this. Which light shuts off? I put a valley right here. I cut that part out. What light shuts off? The 10. Does the 30 shut off? It doesn't, right? Because it still has a closed path for it to go. Let's say I put a cut right here between the 10 and the 30. Both of them shut off, right? Because there's now no more closed loop. Your house, parallel or series circuit? Parallel. It would really stink if a light bulb went out and your entire house shut off, right? Old Christmas lights used to all be in series. So you either had to go looking for that one light bulb that was out, or you had to just replace the whole set. Now they're in parallel. Just know there's a lot more wire in it because you need to run all those through, right? So you can have series, you can have parallel, you could have a combination of both. This would be a pretty simple, complex circuit. You have parallel pieces because we have separate branches, but we also have series right here because these two are in a line. Does that make sense? Okay. So this is more like what you would see in real life. Okay. Electronics. Combination of series and parallel, depending on what you need. Okay? Make sense? Okay, so those are the two different things. All right, cool. So I'm going to have you spend a few minutes working on these other bits of Tipper stuff, all right? And then we're going to practice resolving series, parallel, and complex circuits. Okay?